let's get to it. So, aujourd'hui, we're going to start talking about power series. So, if I have a sum, right, and what we've considered thus far would be something like that, sum of some a sub n from n equals 0, 1, whatever, to infinity, okay? Great. But what I'm going to do is I'm going to tack on an x to the n thing. And so what this is going to look like is, well, if I just listed out terms, it looks kind of like a polynomial, right? In the sense that I've got number times x and x squared and x cubed and so on. Okay, but what makes this different from a polynomial? Pray tell. What makes it different from a polynomial is I don't stop, right? So polynomial, you get to some biggest power eventually, right? It could be x to the 1 million or something, I don't know. Um, and that's fine. But this thing basically never stops, so we call it a power series. And what we want to do is investigate under what circumstances do these things converge and diverge, and also why are they really handy for certain things. Okay, yeah. So that's the idea. And in this case, we say that this dude is centered at x equals 0, but I could center it anywhere else by doing this. I can just replace the x to the n term with x minus something, okay? And all that does is basically shift it so that the polynomial's sort of base point is at x equals c instead of x equals 0. Now, for practical reasons, many times we center it at 0. There's a certain utility to that, but we don't have to theoretically. Okay, so basically, so let's look at a quick example. All right, so let me say I have 2x to the n, which I'm going to rewrite this like so. Either way, I mean the same thing. Okay. All right, so that's a power series because it has an x in it. But let's pretend that the x is just some number whose value we don't know. Okay, and that's kind of how we're going to treat this. If you saw parentheses something to the n, right, which is the first way I wrote the series, what kind of series would you think, that looks a lot like a what sort of series? Yeah, I'll take geometric for 400, Alex, right? Because what does a geometric series look like? It's something raised to the nth power, right? And then sum over that thing. Okay, so this looks geometric. Okay, great. Looks geometric. Well, if we've established that it's a geometric series, what stuff do we need to be interested in for a geometric series? What are we worried about? I mean, because of course the whole game here is, right, does this thing converge or not? What, n? Or what do you mean? Not n, because n goes from 0 to infinity. What did we call that? Yeah, what's the stuff that's getting raised to the power? What did we call that? It's a pirate's favorite mathematical variable. R, right? Okay, so what's the common ratio here? Well, it's the thing that gets raised to the bigger and bigger powers, which in this case is the quantity 2x, whatever that is. Does that make sense? It stands for, as we're going to find out, radius. Okay, and we'll see that today, right? Okay, so what's got to be true about R for this thing to converge? Well, the ratio R, or actually there it stands for ratio. We'll talk about radius here in a minute. They're related but not identical. That ratio has to be less than 1 in absolute value, right? The thing that's getting raised to higher and higher powers. In this case, 2x is that ratio, yes. Okay. All right, so in this case, we require well, here, let me write it this way. I need a little bit more space. Okay, so what this means is for this thing to have a hope of converging, or sorry, for it to converge because it's geometric, we require that the thing that gets raised to bigger and bigger powers be less than 1 in absolute value. Okay, so that tells me that 2x needs to be less than 1 in absolute value. All right, and then what I want to do is say, okay, absolute value of 2x less than 1 is an inequality. Well, you guys dealt with those things in algebra, right? So what does it mean for the absolute value to be less than 1? It means that the thing is between -1 and 1, right? So an absolute value inequality really splits into a pair of inequalities. And then I'm going to sort of solve each one to get x by itself. And in this case, that's easy. All I have to do is divide by 2. And so 2x is less than 1 in absolute value is equivalent to saying x is between -0.5 and 0.5. Okay, and strict inequalities on those. Okay, does that make sense? Yes? Okay, so this quantity 1/2 is called the radius of convergence in this case. Okay, so think about it this way. Between -0.5 and 0.5, how long is that interval? 1 unit, right? So if I pretend that that's a diameter, well, what's half the diameter? The radius, and in this case, that would be the number 1/2. So we called that the radius of convergence. Okay, so it's sort of how far away from 0 can x be, and you still get something convergent. Okay, and that's why we call it a radius. Now, the other reason we call it a radius, and this is something that those of you who continue with lots of math will get to see, is here. What kind of values of x am I considering? What the variable x? What kind of variable is it? Huh? I heard it. It's a real number. Does it have to be a real number? No, of course not. And if we do this with complex valued variables, okay, so things that include our favorite square root of -1, and you look at in the complex plane, the region of convergence, it literally is a circle. And hence we talk about a radius. Okay, so that's why we use the word radius here, because it's in the complex valued case, it really is a circle. Now, those of you who choose to go on, you would learn about this in a complex variables class, which is Math 3 something or other. Cole, you're totally going to do that, right? Yep. No. Yes, no, maybe. Well, that's the entire point of the course, is basically how do you do calculus when imaginary numbers are involved? Uh, certain things are really weird and certain things are really nice. Okay, so I'll give you an example. Um, is it possible to have a function that you take the derivative of it and that derivative is no longer differentiable? Or better point, is there an example of a function that you cannot take the derivative of, meaning it's not differentiable at a point? What's a good example? Yeah, Jack? Huh? Yeah, okay. Now, give me one that's continuous but not differentiable at a point. Hmm? Yeah, it is. Absolute value of x, right? It's part, everything's fine except where? At 0, where you've got that little point. Yeah, cusp. Okay, not cups, cusp. Okay, so I can make a function be not differentiable at a point, right? And I could make another function be not differentiable at 2 points. I could do like a zigzag type thing, right? Um, there is actually an example of a function that's continuous everywhere and differentiable almost nowhere. Or yeah, and there is a technical meaning for almost nowhere in mathematics. It's actually really cool. Um, so you could have a function that you could take the derivative of 5 times and then suddenly the thing is no longer differentiable, right? That totally can happen. Or I could have a function where I could take the derivative of it once and then it's no longer differentiable. What would that thing be? Well, it'd be the antiderivative of the absolute value function. That'd be an example, right? It is. Yeah. And they actually do talk about the fourth, fifth, and sixth derivatives. So so yeah, velocity is the first derivative, acceleration is the second, jerk is the third. Guess what 4, 5, and 6 are called? No. Snap, crackle, and pop. Yes. I am not making that up. There's more than 3 humans, but yes. They do call them snap, crackle, and pop after. Yeah, no, they mean something in certain contexts, yeah. Okay, so anyway, I could come up with a function like the antiderivative of absolute value of x would be only once differentiable because I'd take the derivative of it and I'd get absolute value of x, but then that thing's no longer differentiable because of that one bad point. It turns out in complex numbers, if you have a function of complex variables, the notion of differentiability is a little different, but it becomes the case that if you're differentiable once, you're differentiable infinitely many times. So the example that I just said with absolute value doesn't apply in the complex world. And that's like really cool. All right, anyway, if you want to learn more, go on to be a math major. Okay, so, right, so we got our interval of convergence and our radius of convergence. Now, what tests are you going to be using to work with these power series? Well, they're going to be the things that give you inequalities that involve an absolute value, which are the ratio test, the root test, and the geometric series test. Okay? So those are going to be the ones that we'll really use quite a bit in our work with power series. Okay, good. All right, so continue A. All right, so what did we just do here? We defined the interval of convergence. So what's the interval of convergence in our example where we got it from -1/2 to 1/2? That's the interval, right? It's 1 unit long. Okay, the fact it was 1 unit long is sort of just whatever. So the interval is negative a half to a half, and the radius is half of that length, which in this case is just the number 1/2. Okay, so that's the rules here. Okay, so if I have a power series, right, and here I do, there are three possibilities that could happen. The series could converge only at the center point. The series can converge on an entire interval, or it could be the case that it converges for all values of x. Okay, and we'll see some examples where it converges for every value of x, which is nice as we go. Okay, so in our case, which situation did we run into in this particular example? We ran into it where it converges inside an interval and it diverges outside that interval. Okay, so for example, if x equals 1, then what is our series? It's the series of 2 to the n, and does that thing converge or diverge? Series 2 to the n. Well, what does 2 to the n do if n goes to infinity? It big time diverges. Okay, so right. Okay, so we'll look at some more examples here. Do you guys mind if I move to the next a new screen on the iPad? Is it okay? Here, yes. Okay. All right, so let's try this one. Oops. Okay, so Dr. Insaldi claims that we can't use the root test. She wrote the sheet thing for today. That we can't use the root test and we can't use the geometric series test for this one. So let's make sure we understand why. First off, why can't we use the geometric series test here? So take a minute and kind of think about that. Maybe those of you guys who are online can like Farden or Coy or get affiliated now. Yay. Uh, kind of, but so Cole just said because there's two ends, sort of, but elaborate. I mean, you're barking up the right tree there, but not quite. You like I said, you're barking up the right tree, but the other ideas, Jack? Yeah, exactly. So this thing isn't geometric because what makes it geometric? Constant times constant to the power. But what's the coefficient term here? N. That's not a constant. So this thing isn't geometric, right? It's sort of almost geometric because we got a something to the n, and it would be if it weren't for that n out front. But we got that n out front. That's not a constant. Okay, so it's not geometric. She also says the root test won't work here. Why won't the root test help us? Oh, you could, Farden. It would just be really painful to do that. So Farden says we can't expand the bracket, meaning the parenthesis term. Could we FOIL that stuff out for You could. Do you want to? Not for very large values of n. No, that would be torture. Uh, I don't know. Just try it. But you don't want to even try that though, because for large values of n, it's going to be ridiculous. Hmm? Okay, fair point, right? So the root test, when we first defined it, we said that the root test only applied to positive sequences, and that's true. Um, but we have something that could be positive and negative. It depends on the value of x, right? So there's a slight modification of the root test where, so what do we do in the root test? We take the nth root of a sub n. Well, do this. Put an absolute value bar around the thing and take the nth root of that. Then you can work with alternating series too. Okay, but the reason that's not going to work, right? The nth root of x minus 5 to the n, all right, well, that'll be nice, but with the nth root, I don't know what that thing converges to, okay? It's not going to help. And in fact, I think it would actually go to 1, which is not helpful. However, the ratio test will be our trick here. So what do I need to do in the ratio test? Okay, and isn't that the ratio test, right? You do a sub n plus 1 over a sub n. Okay, now what's the one thing I've added here that we didn't have before? Well, I put the absolute value there. Okay, so this is, if you guys remember when we first started talking about the ratio test, and I said, well, you know, it's actually kind of, this isn't quite right because there'll be a modification to this later. That modification is the absolute value because this means we can talk about it for uh, sequences that are both positive and negative, or series, excuse me. Okay, so I'm going to do this thing, and what do I want this to come out to be for convergence to happen? What's the ratio test limit need to be for us to have a convergent thing? Yes. Um, the ratio test limit. It needs to be less than 1. Okay, if it's equal to 1, then it's inconclusive. If it's bigger than 1, then it's divergent. And if it's less than 1, then that means the thing is absolutely convergent. Okay, that's why I put the absolute value in here. Okay, so we got some algebra to sort out to be able to take this limit. And I'm going to put this in 2 pieces. I'm going to split it into 2 terms, one of which has got all the n's in it, and the other of which has all the x's in it. Okay, first off, do you guys agree that I have correctly split this thing up? Like I haven't flubbed the algebra? Because it's, of course, you know, they'll just hire anybody to teach math around here. So, you know, you have to deal with this silly McKinney guy. Well, yeah, because what are the powers? I've got one bigger on top than on bottom, so all but one of them cancel. Okay, and then n plus 1 over n, well, whatever, that's just a fraction. Okay, now, the reason I split that is because if I'm taking the limit, does the x minus 5 have anything to do with it? The limit? Or taking the limit, let me rephrase. No, because does it have any n's in it? No, okay. And what is the limit of this part? 1 by y. It is, right? It's 1 by L'Hopital's rule, or, you know, other techniques, but it is 1. You know, humor me, Will.
It just is.
Huh?
It just is.
No. It means I can, yeah, it is what it is, right?
It is what it is.
We know this. Anybody guys watch the Saturday Night Live last weekend? No? Saturday Night Live on Saturday? Oh, well, the Weekend Update, which is like their fake news show, right? No, that well, sort of, but I mean, it's Saturday Night Live. They have to make fun of something, and politics is ripe for the picking in terms of comedians. Yeah, it's like they're writing. Yeah. Anyway, all right. So that goes to 1. So this limit is literally just x minus 5. Okay, so convergence happens if x minus 5 is less than 1 in absolute value, right? So what did the ratio test say? That limit needs to come out less than 1. Well, what did the limit come out to be? X minus 5 absolute value. So we require that that thing be less than 1. Okay, this, like before, is going to give us an interval and a radius. Okay, so what's the interval? Well, careful, because it's x minus 5. So let's, I know, arithmetic's hard, because I add 5 to both sides, right? Yeah, okay. All right, so basically I just split the thing up into 2 inequalities, right? And then I added 5 to both sides, or all 3 sides, I guess, because it's sort of a triple or double inequality. I added 5 to everything, damn it, right? Uh, and so this thing will converge if x is between 4 and 6, okay? All right, so what's my interval of convergence? It's 4 to 6. With soft brackets for now. We'll worry about the, yes, parentheses. We do. We're not done yet. Silence. Yeah, exactly. I can't. Okay. So, yeah. All right. So the interval so far is 4 to 6. Okay. Does that make sense why it's 4 to 6? That's why we did this whole inequality business. All right. So what's the length of that interval? How many units is 2? Okay. Yes, it is 2 units long. And therefore the radius is half that, which is, okay. Yes. Okay, guys, and you guys wonder why you know, I both love my job and why I drink large quantities of bourbon on the weekends, right? Because of the love I get from my students. Huh? It depends. If I'm mixing, I usually use Jack or Makers. If uh, if I'm mixing a fancy cocktail, then use something like Buffalo Trace or Knob Creek, like an old fashioned or something. Uh, if I'm just sipping it, then actually those are good sipping bourbons too. Um, yeah. So now that the weather's turning colder, though, I tend to drink a little bit more scotch because it's got that peatiness to it and makes me feel like I'm in a stone cottage in the Highlands of, I guess. Yeah. Anyway. All right. So, no, it didn't. Sorry. you need to work on your delivery there, Cole. Um, so, okay. Um, Now, when I say the interval convergence is 4 to 6, we're not quite finished yet. Okay, and what I mean by that is the theorem that we talked about a minute ago doesn't tell us what happens at the endpoints. Okay, so what we have to do is check those manually. So if x equals 4 actually equals 4, we don't know whether or not the thing convergence or not. Okay, and let's think about why. Because if x equals either 4 or 6, and I plug that into my to here, what's the absolute value of x minus 5 going to be if x is 4 or 6? 1, which is where the ratio test is inconclusive. In, not quite. So Cole said indeterminate. I would quibble there. And this is super like nitpicky, right? Limits are in indeterminate forms. Tests are inconclusive, right? Don't you love English? Yeah. I was gonna say you two probably think it's the silliest language ever. No. Um, huh? It is because it only has 26 characters for the most part. No accents or any other dangly bits. I mean, uh, well, decorations. Well, I mean, you think French or Spanish is bad? You should see Vietnamese. Oh, there's lots of dangly bits. Yeah, and then there's Chinese and Korean. I mean, at least Korean, right? You have the Hangul, right, which is somewhat regular, but um, but Chinese is just off the deep end, right? Because how many characters are there in Chinese? Like, well, a traditional Chinese, say, thousands, thousands upon thousands. Yeah. So anyway, all right. Well, so what we need to do though is because x equals 4 or x equals 6 make this ratio test limit equal to 1, the ratio test doesn't tell us anything there. So we have to examine those cases separately. Okay, so let's take x equals 4. Now, our original series was this. If I substitute x equals 4 into that, then I have this. Negative 1 to the n times n, right? Because last time I checked, 4 minus 5 is negative 1, and that's the part that got raised to the power. Okay, good? To what now?
I can't understand how it.
Oh, replace x with 4.
Oh, I see.
Yeah? Okay. Okay, so we clear how I got that second series. I just took the first one, the original series, and I replaced x with 4. And 4 minus 5 is negative 1, so that's why I've got negative 1 to the power. And then that n is still there, right? It is an alternating series, but does it converge is the question. Well, let's check it. Does the alternating series test apply here? What does the alternating series test require? Mm-hmm. But yeah, but is a sub m decreasing? What's the limit as n goes to infinity of n? L'Hopital rule U.
Can we get one before?
No. Well,
What did we get then?
well, we haven't done it yet.
Oh, what is the limit of n?
Yeah. If n goes to infinity, what's the limit? Right. So the alternating series test requires that the non-alternating part be decreasing and have a limit of 0. However, is this limit 0? No, big time not. Because what is that limit? A big ass infinity. Yeah, exactly. So the series at x equals 4 diverges. Them's the break. It happens, right? Sorry. Yeah, rip.
Half in the chat. Or no, half the papers.
Yeah. Well, I mean, we are on Twitch, right? So I don't know. Maybe we'll get a GG or a rip in the chat. Be sure to like and subscribe. Donate bits. Um, I know.
I was playing online video game, NBA 2K, and I was beating this guy, and then he paused it right before the game's over and gave me a 2-minute speech on how I was the scum of the earth. I thought that was interesting. Like he went real in depth on like how bad of a person I was. I hadn't even talked about me. It's a sad life.
Yeah. Well, this is why we cannot have nice things. Yeah. Okay. So we did the case when x equals 4, but we still have to check the same idea if x equals 6. So same idea, I'm going to substitute this time 6 in, almost the same thing. Well, because what's 6 minus 5? Not negative 1. Okay, so this time though, but what's 1 to the n? It's always 1, right? So now I have something that's not even alternating. It should be easier to figure out because we don't have to worry about the alternating series. But what does that series do? It big time diverges. Why? Huh? Because that limit is not 0. Uh, as a sequence or as a series, it diverges. Uh, you mean it's just n? Yeah. As a sequence or a series? As a series, it diverges, but you can't say to you can't. Right. Okay. It diverges because the limit of the sequence of partial sums is not a constant, is not a value. And for negative 1 to the n, your terms are 1, negative 1, 1, negative 1, and so on, which means, hold on, I'm not done, which means your partial sums are 1, 0, 1, 0, 1, 0. What's that sequence? Does that converge to something? Nope. So that means the series diverges. It does. That's what I was just looking at.
Oh.
Right. Okay. So, all right. So this series also diverged. So in this case, our interval of convergence stayed roundy brackets or round parentheses 4 to 6. Okay. It is possible, if I had picked a different series to start with, that it could have converged at one end but not the other. It could have ended up converging at both ends, or it could have not converged at both ends, which is what we had here. All 4 possible cases can occur. Just depends on the original series. Okay. Um, yeah. So yes. Okay. So it is possible that when you do this, one of them will converge and the other one will diverge, or vice versa, or maybe both will converge. Who knows? Right. There are examples of all of those. Okay. And this is why, of course, you guys get to do exercises. Okay. All right. So let me see what else we need to do. That's what we did. We handled the values separately. Okay. And then we basically want to do more examples. Okay. All right. Now, the thing we'll sort of conclude with today, this is really cool. All right. So let me go to a new sheet here. Let me take that guy, right? That's geometric, right? And what we were just sort of doing was determining under what values or what circumstances, so what values of x, does this thing converge or not? Okay, fine. Good? All right. But this thing is geometric, isn't it? So if it converges, we can actually say what it converges to. Right? So what does it converge to? So if you have a geometric series, what does it converge to? First term over 1 minus the common ratio. And what is the common ratio in this example? X. Okay. So this is, I can say the following. I can say that if x is less than 1 in absolute value, then that series converges to 1 over 1 minus x. Okay? Which means if I have a function 1 over 1 minus x, I can represent it using a power series. That's going to be super powerful, pun intended. Okay? Now, if this is x to the n, could I replace x with something? So for example, if I had right? But does it matter what smiley face is? No, that could be any formula in terms of x. I just have to substitute in. Okay. So what this means is that starting with this guy, I can use it to come up with power series that represent lots of other functions. Okay. So if you have a function, what are the things you can do to transform it into other functions? Well, you can make substitutions, which is what I did with the smiley face. Couldn't I multiply things by x or divide by x equivalently? Yeah. And this being a calculus class, I can take derivatives and integrate. Okay. So what could I do with this series? So let me take this dude here. Well, here, let me highlight it in a color. All right. So let me actually, let's take that. 1 over 1 minus x. Let me call that f. What's its derivative? Is that the correct derivative? How many of you think I'm missing a minus sign? Right? So negative 1 pops out front times that stuff to the negative 2 times another factor of negative 1 because of the chain rule, right? And two negatives make a plus, so that's why it's that and not what I did. Okay, so let's use our noodles here. Our noodles, right? Our brain noodles. Man, your mind's in the gutter, Mr. Trap. Huh? Just clarifying. Oh, right, or like a giant pool noodle? Yeah, okay. Yes, Jack. Hmm? On that, yeah, you could, right? Um, Now you get exactly the geometric series test out of it, right? Because it's a special form. But yeah, you could use the root test. So here, I have that 1 over 1 minus x is equal to this power series. And I have the derivative of 1 over 1 minus x is that thing. How do you think we could come up with a power series for this dude, for the derivative? Well, what do you think I can do to the power series that I started with? Why don't I take its derivative? Okay, so let me write that out carefully and you'll guys will see what I'm up to here. All right, so I have this. Oops. Yes? Okay, so if I have equals there, can I do the following? If two things are equal, shouldn't their derivatives be equal? That makes sense. Okay, what's the derivative of the thing on the left? That. Okay, here's where I'm going to be technically sweeping a technical thing under the rug. Trust me, I'm a doctor. Okay, now let's think about why this makes sense. If you had the derivative of 5 functions added together, how would you compute that? So if I wanted you to take the derivative of x plus x cubed, what would you do, Jack? Mm-hmm. Yes. Okay. Now, for finite numbers of things added up, that's obvious, right? I claim that it actually holds even for an infinite sum. That's the technical detail I'm sweeping under the rug here. Okay. Trust me, I'm a doctor. I'm allowed to do this. And what's the derivative of x to the n? Okay. Well, now I've produced a power series that represents this other function. Okay, and I've done so by starting with a known power series and doing some either algebraic or calculus. That's a new technical word here. Calculus, right? So what have I done, right? I took a known power series for a known function. I did some trickery. In this case, the trickery I chose to use was the derivative. And I have produced a new power series that is equal to a new function. Well, could I have integrated instead? Could I do the 17th derivative?
Sure.
Yeah, I could do all kinds of algebraic or calculus trickery. Why? Because, okay, because what this will let us do is build up a library of power series for commonly encountered functions. Okay.
Substitution for this.
Well, that's coming, right? So that's what we're going to do next time is we'll talk about a secret method for figuring out coefficients to build power series. Okay, so I will initiate you guys into the club of Taylor, right? The cult of Taylor. All right, so that's the idea here, right? Is starting with a known power series, we can cook up the power series for a different function by means of algebraic trickery and doing calculus. Okay? All right, I've gone way over time. I'm sorry. I will see you guys on Friday.